Hello, Physics 341. Dr. Eaton here, and we are going to go through the practice problems for lenses here. I'm going to give you a step-by-step guide on how to solve all of these problems so that you have a nice key we can refer to as we're studying at home. So the first problem here, it asks us to look at the properties of both a convex and a concave lens. So we're just going to step through those little by little to sort of look at how these lenses work and what kind of images they form. So a convex lens bubbles out on both sides, so it looks kind of like a lemon in shape. And what a convex lens is a converging lens. So if we have light rays coming in all parallel to each other, those light rays will bend and they will converge in on each other at a point, which is none other than the focal point. So this is a converging lens. And it's characterized by having a positive focal length. So this F distance is always going to be a positive number, and this focal length does exist on both sides. The kinds of images that are going to form are going to depend whether or not the object starts inside or outside of the focal length. So if we are outside of the focal length, our image is going to be real. So light's going to shine through and the image is going to form on the other side. So for a lens, we expect light to shine through the clear glass, for example, and the image is going to form on the other side. So a real image, unlike a mirror, is on the opposite side of a lens. It's also going to be inverted. It's always going to be flipped upside down, and it could be magnified or reduced depending on exactly where it is. So it could be either one. We don't know for sure until we actually do the calculations. If we are inside the focal length, this one always has a set of definite image properties. It's always going to be virtual. You have to look through the lens to see the image formed. It's always going to be upright, and it will always be magnified. And so the example of a convex lens inside the focal length is your traditional magnifying glass. So if I have an object really close to my lens that I'm holding and I'm looking at it, I will see that object in the lens the same way it was before, but a lot bigger. So this is a magnifying glass. So that's our convex lens. A concave lens is shaped like an hourglass. And again, just like the other one, it has a focal length on both sides. This is a diverging lens. So the light rays are still going to come in parallel, but instead of converging to point F like they did above, they're going to spread out and get further apart. A diverging lens means that F is negative. So if you have a diverging lens or a concave lens, that automatically means your F value is going to be a negative number of whatever that distance is. For whatever kind of image or wherever you place the object, inside or outside the focal length, a concave lens is always going to form an image that is virtual. You have to look through the lens to see it. It's going to be smaller, or reduced as we call it in lens speak, and it is going to be upright. So a concave lens, you're always going to have a smaller virtual upright image, but you cannot project that image anywhere onto a screen. So a concave lens, you have a negative focal length, it spreads the rays out, and it's always going to be virtual, smaller, and upright. So now let's see how we can solve problems concerning lenses here. So this first problem here, we have a 3.5 centimeter object, 3.5, is placed 18 centimeters from a convex lens. We want to know where the image forms, the image location, the magnification, and the height of the image, how tall that image appears to be. And this is going to be the order that we're going to kind of solve for these things each time we do a lens problem like this. So we're always going to get image distance first. So it's sort of like 1. The next step is we're going to find the magnification using the image distance we just found, and then we're going to get the height. And this is a very typical way to tackle these kinds of problems. So let's figure out what we know. We know that the object is 3.5 centimeters itself. So this is referring to the height of the object. We also know it is placed 18 centimeters. And I should have written down before that the focal length is 12 centimeters. So we have the focal length as 12 centimeters. So our first goal is to find the image distance. We're going to use our lens formula, which looks a lot like our mirror formula from before, so nothing new here. We have 1 over f equals 1 over do for the object distance plus 1 over di for the image distance. So now we can plug in our numbers. We know we have 1/12 equals 1 over 18 is our object distance. We're not going to use our image height or object height just yet. And that's equal to 1 over di. So I got to rearrange this. We're going to get 1/12 minus 1/18 equals 1 over di. So we plug those into our calculator and we get 0.0277 equals 1 over di. So we're not done yet. This is the most important step. We have to flip both sides. So di is equal to 1 over 0.0277, and that is equal to, we get about 36.1 centimeters. So that is our di value. We can now use this to get the magnification by looking at m equals negative di over do. I plug in my value, I get negative 36.1 divided by 18 was our original object distance, and this is a little bit bigger than 2. So it's about 2 times larger. The negative sign here tells us that it is upside down. The negative sign does not mean it is smaller. So our magnification is negative 2 times. Lastly, we want to get the height. All we want to do is the height, or the magnification is also just the height of the image over the original height of the object. So that's the same as multiplying our magnification by the original height. It's telling us it's that much bigger or smaller, and that's going to be 2 times 3.5 centimeters, which gets us a nice even 7 centimeters tall. But it's inverted, so it's upside down. You can write negative 7 centimeters or just leave it as 7 if you know that it is in fact inverted. So that is our typical lens problem. We're going to get the image distance, we're going to calculate the magnification, and then finally we're going to use the magnification to get how tall that image looks. All right, moving on. Problem 2 is very similar. We have a 4 centimeter tall light bulb placed 8.3 centimeters from a convex lens of focal length 15.2 centimeters. We want to determine the image distance and size. So the size is the height here. We're not explicitly told to find the magnification, but just like before, we're going to need that magnification to get the size. So we're going to get it along the way. So same kind of thing. Let's figure out what we know. We know that 4 centimeters is the height of the image. It's 4 centimeters tall, so that's our HO. Our 8.3 centimeters is how far the object is placed, so that's our object distance. And the focal length F is explicitly said to be 15.2 centimeters. So we know all that info. We're going to use our lens formula again. 1 over F equals 1 over DO plus 1 over DI. DO is 8.3. Our focal length is 15.2 plus 1 over DI on the other side. We can try to simplify this or rearrange this. We'll get 1 over 15.2 minus 1 over 8.3 equals 1 over di. And we can put the left-hand side of our equation into our calculator. And what we get there is negative 0.055 equals 1 over di. We've got to flip it again. And so when we do that, we get a value of about di is equal to 18.18 centimeters, and it's negative. That negative sign tells us that this image is virtual. All right, we've got di, that's our first part, so we've got the image distance, check. We need to find the magnification to get the size, so same thing, m equals negative di over do. When I plug the negative di into this formula, this original minus sign in the formula itself cancels out. And so we get positive 18.18 over our original image distance of 8.3. And that turns out to be 2.19. So it's 2 and then some times larger than it actually was. Here, the fact that this number is positive means that it's upright. So now all we're going to do is we're going to get the height of the image by multiplying 2.19, our magnification, by the original height 4. And that is going to get us a final value of 8.76 centimeters tall. All right, let's keep this train going. Now we're going to determine the image distance and height. So same kind of thing we just did for a 5 centimeter tall object placed 20 centimeters from a double convex lens of focal length 15 centimeters. Double convex is just, it doesn't really mean anything. A double convex lens is exactly the kind of lens we've been using all along. It's convex on both sides, and hence they call it a double convex sometimes. Don't be too tripped up by that. So same kind of thing. We know that the height of the object is 5 centimeters tall. We know that the object is placed 20 centimeters away from the lens, and the focal length is 15 centimeters. All right, same kind of thing. 1 over f equals 1 over do plus 1 over di. We plug in our numbers, we get 1 over 15 equals 1 over 20 plus 1 over di. And then we're going to subtract 1/20th from both sides to get 1 over di all by itself. Plug that value into our calculator. And we get that 1 over di is equal to 0.01667. And we got to flip it to get a final image distance of about 60 centimeters. So this image ends up pretty far away compared to where it really originally was. Got to get the magnification again, negative 60 divided by 20, our original value. And that's a nice even 3 times. So again, it's 3 times larger, but the negative sign tells us it's upside down. We can finally get the image height. HI is equal to our magnification, negative 3 times 5 centimeters, and we get negative 15 centimeters, or just 15 centimeters inverted. Those are 2 ways of saying the exact same thing. All right, we're starting to see a process here, I hope. Our last problem is going to switch it up a little bit on us. Here we have a magnified inverted image located 32 centimeters away from a double convex lens with focal length of 12 centimeters. So here we're told the image is located 32 centimeters away. So we're actually starting with DI and not DO like we have been for the past 3 problems. So we want to now find the object distance, DO, and we want to know if the image is real or virtual. So we don't have to do a whole lot of work. We talked before about for a convex lens. Let's take a look back at that. If the image is inverted, that means that the object, the image is going to be real. So an inverted image from a convex lens necessarily means that the object is real. So we know that the image is definitely real because it's inverted. And we now want to calculate the object distance. So, hey, we know F is 12 centimeters. We know that the image distance is 32 centimeters, and we're trying to find the object distance. Well, hey, we got a formula for that. 1 over F equals 1 over dO plus 1 over di. We have 1 over 12 equals 1 over dO is our variable this time, plus 1 divided by 32. So same general process. We're going to subtract a 32nd from each side, and we get 1 over dO by itself. So we can, it'd be nice if you could see what I'm writing here. We now have 1/12 minus 1/32, and we plug that number into the calculator to get 0.052. We still got to flip it, so 1 over that value is equal to dO. Finally, the thing that we want, and we get a value of 19.19 centimeters. And that should do it. So this is our key for our lenses practice problem. If you have any further questions about these, please reach out to either myself or Mrs. Jenkins, and we can help you out there. So I hope you found this useful, and good luck.